Polar coordinates are an alternative coordinate system, and in this lesson I'm going to show you how you calculate area and mass using this alternative coordinate system. But the big picture takeaway here is actually to think of alternative coordinate systems as a parameterization. That is the ultimate goal. How can we measure volume and mass when our objects are described parametrically? The first thing that you have to do when you start measuring space in an alternative coordinate system is figure out what the area differential is. So that's going to be the small amount of area that's produced if you change the variables by some small amount. So in polar coordinates, the variables are r and theta. So dA is going to be the area of the region that's produced by changing the radius by dr and changing the angle by d theta. May have been a while since you took trigonometry, but I swear you have seen this somewhere before. We have a formula for the length of an arc. If you have like a little piece of a circle, then this length right here, that length right there along the circle, we're going to call that S for arc length. That's consistent with our use of the letter already. Then the formula is pretty simple. It's just R times whatever the change in theta is. And that's pretty easy argument to see. In this, you have to make sure that theta is in radians. Obviously, it's not going to be like R times 360 or something. All right, so we can use this formula actually to get the area differential. So the idea is, if you're like at some point right there on the polar curve, and you changed the radius by some amount, then you would go out some maybe small amount like that, and then you're going to change the angle by some amount, so that's going to go over right there. So in polar coordinates, this little darkened in patch right there, that's going to be what we call dA. I think you can see already what the issue is. If I pick a dA that is very close to the origin, or I pick a dA that is farther away from the origin, then the size of that little rectangle is going to be different. So we can actually use this formula to construct the area differential in a pretty simple way. I've drawn the little polar patch. So there's that little piece right there, the surface area differential in polar. And so we're going to change r by some amount. So I put dr along this corner right here, and we're going to change theta by some amount. So I put theta over there on that piece. And you can see that this little polar sector is approximately a rectangle. And actually, the smaller that I made dr and d theta, the smaller this rectangle would be. So that's it, you know. So the area of a rectangle is you just multiply the length times the width. So it's just going to be r dr d theta. So there it is. We've done it. The surface area differential. So what does this mean to you? This means that in polar coordinates, remember the area, just in general, the area is going to be 1 dA. So if you're calculating this in polar coordinates, it's going to be the double integral of 1. And then instead of just using like dx dy, there is now going to be an r dr d theta. And that r just comes from this piece right here. It just comes from this calculation right here. And all we're doing is accounting for the fact that little polar patches that are closer to the origin are smaller than polar patches that are farther away from the origin. So, I mean, basically what this means is, you know, if you're solving a polar double integral problem in a Calc 3 class, you just got to stick that magic r. There's just an r that just gets produced in your formula by this process. I want to point out this note right now. This isn't going to help you calculate areas in polar coordinates, but it is going to help you later when you start changing coordinates in other ways. When you change coordinates, you are changing the size of little rectangles. So since our rectangles are a different size, and we're basically like counting how big the rectangles are, you're going to have to compensate for that fact by multiplying by some scaling factor. And we have a name for that scaling factor. It's named after a person. So we're going to call it the Jacobian. In this setup, the Jacobian is just going to be r. And usually it's a very simple thing. And you've actually done this before, all the times before in your life when you were doing u sub. If you had something like u is equal to 3x, then du would be 3dx. So in that process, that scaling factor 3, that was what we're going to call the Jacobian. So, I just want to put that in your mind as early as I possibly can, that whenever you change coordinate systems, you're always going to have to calculate area in a different way. You're going to have to rescale your answer to account for the fact that maybe your little pieces are now different size than they used to be. Okay, I think I've come up with a pretty good example. I like this problem because this is a problem that I think you would really, you pretty much have to have polar coordinates in order to figure this out. I've got a semicircular plate here. The radius is 3, and it's only the part of the circle that's above the y-axis, and it has variable density. The density is e to the negative x squared minus y squared, which should be causing you to kind of panic here because, we can't do these antiderivatives. Okay, so let's do it. We're asked here to find the total mass. So if we look at the area of a small patch, dA is going to be r dr d theta. So then dm, the change in mass that comes from changing r and theta a little bit, is just going to be delta times r dr d theta. Okay, so that tells us the area of a small piece, the mass of a small piece, and if I add all those up, I'm going to get the total mass. Okay, so the total mass in this problem is going to be the double integral, and these integrals are now going to be in terms of r and theta. So we're used to writing like x and y values. Now I'm going to put r values on these and theta values on the outside integral. Okay, so and the things that I'm adding up are the density of each piece times the area of that little piece. Okay. All right, so we've already got in a little bit of a conundrum here because my units disagree. You can see that this is x and y, and that's r and theta, but I made this up, so it kind of comes out in a nice way. You can see negative x squared minus y squared is really just negative r squared. Okay, brilliant. And now, what are all the radiuses? So all of this distance right there, that is going to be included because it's inside the region. So I want to add up all of these little masses for each value of the radius in between 0 and 3. Now for theta, I'm not going to go all the way around because that would do the whole circle, and I don't want the whole circle. I only want the values between 0 and pi because that gives me the part of the circular plate that is above the y-axis. Okay, so let's look at this little integral that we've set up here, and I think that you can see pretty quickly that we can solve this inside integral with a u sub. U is going to be, I guess I'll do negative r squared. And I'll work out this answer and actually spit it out, but I'm going to do that off camera. At this point, I think the interesting thing for you to realize is that we've really sidestepped a huge mathematical problem here because there is no antiderivative for this. If you start trying to find antiderivatives in terms of x and y, you're just stuck. There just literally isn't any. And then boom, when we switch it to polar, this like kind of magic r that's produced there from our arc length formula makes a whole class of math problems that would be previously unsolvable. Well, yay, now we can solve them. So that's the point of this example. It's kind of beautiful. Let me just go ahead and work out the answer. Okay, so I just did some fun math here and ended up with pi over 2 times 1 minus e to the power of 1 over 9. I guess kilograms, because this is mass. Okay, so this is kind of great. Once you change these things into polar coordinates, a lot of times the integrals just fall right out. The difficulty usually from the student point of view is actually being given a region in rectangular coordinates and then changing it into polar. So let me jump into some of those examples really fast. I just kind of want to justify my picture that I drew over here. You can see like I have a whole bunch of dots, and the bigger, this is like, those negative powers there means it's like 1 divided by e to the power of something. So the bigger number that you plug in for x and y, the smaller the density is going to become. That's why you can see here I have it kind of shaded in dark close to the origin, and as you get farther away, the object becomes less and less dense. And here's the total mass. That's beautiful, right? Okay, so quick little problem here. We're asked to find the area inside this region, x squared plus y squared is equal to 10. So if we just bounce over to Desmos, we can see a circle there that sits on the positive x-axis, and the radius is 10. Okay, so what does this look like in polar? Well, I think it's pretty easy to change this to polar. X squared plus y squared is going to be r squared. And then 10x, x is r cosine theta, so this is going to be 10r cos theta. So we actually end up with 2 possible solutions here. We either have r is equal to 0 or r is equal to 10 cos theta. And actually that really makes sense in our picture. Actually, since the origin, that point right there is r equals 0, and then all the other points there are also r is equal to 10 cosine theta. So there it is. Now I've changed this region into polar coordinates. So I get a kind of circle like this. All right. Wow, that was like that was a pretty good circle, honestly, the best circle I've drawn all semester. So this is the x-axis and this is the y-axis. So we're still in xy space, and then I'm just graphing this x equals r cosine theta. All right, so I need to set up a double integral here for this area. So I'm going to do the double integral of 1 dA, and since I'm in polar, this is going to be r dr d theta. It just goes into my head as the like pirate formula. You just put the R in there. Okay, so what you do is, before we were imagining our laser beams like going out in the x-axis direction or in the y-axis direction. Now, since our limits of integration are R values, what we're going to do is we're going to imagine a laser beam emanating out from the origin along some ray. So you have to ask yourself, when does the laser beam enter and exit the region? Okay, so this right there, r equals 0, the laser beam starts off inside the region. So I'm going to start off with r is equal to 0. And then what is the r value right there where the laser beam exits the region? That's where r is equal to 10 cosine theta. Okay, now we're going to have to figure out the limits for theta. Okay, I don't want to admit how long I've been working on this little part of it. My original intuition was way too complicated than what it needed to be. So I fixed it now. It's actually pretty simple. All right, so what are we looking for when we're trying to find this area? Well, we've got this kind of circle, right? And what we want to do is, as theta changes, this graph is going to trace out this circle. And I want to make sure that I trace out all of the circle, but I only trace it out once. So you can see that if I imagine the circle starting right there, where r is equal to 0, then, the thetas are going to change, and that's going to go around. And I will have traced out one circle. When I go around again and I get back around to another time that r is equal to 0. So that's what that's my logic here that I'm doing. So I've just kind of constructed this little table. Basically what you want to do is plug in values for theta until you find 2 adjacent times where r is equal to 0, and that's going to trace out the circle one time. In this case, it's also pretty intuitive. You can see this angle right there is when theta is equal to negative pi over 2, and then that angle up there is where theta is equal to pi over 2. So that's what I'm doing. I'm tracing out the circle once around like that. I don't know how this camera may have like mirrored that around. Let me show you on Desmos what is happening here with the r and theta picture. All right, here we go. So made a little slider for this thing to trace the image out. And you can see right here at the very beginning, you can see the blue line, that those R values are very small and then they get bigger and bigger and bigger. Right there where, you know, this actually matches with our little graph. Can you see right here? When theta is equal to 0, R is equal to 10. Okay, let's jump back over to the Desmos picture. Can you see right there that theta is equal to 0 and R is equal to 10, right? I go out like 10 units in the theta is equal to 0 direction. And then as I keep going around, then right when I get here to theta is equal to pi over 2, then that's where I make one full revolution. If I go more than that, I would start carving out the circle again, and I'd be double counting area. So you can see I've even kind of made a little like theta line. So down here is theta is equal to negative pi over 2, and then it goes around. You can see it producing the circle right there, and then boop, back around to the other side. And now we've made the circle once. So that's where I get these limits for theta. Theta is going to go from negative pi over 2 up to pi over 2. That, you know, there's more than one correct answer for this. So really the only way that you can kind of do it is just sort of brute force, you know, get in there, start making a little table for theta, asking yourself, you know, when can theta be 0? What can that be? So that you trace out the shape exactly once. I do want to mention, I didn't work out this whole integral, but I do want to mention that it's pretty common when you are solving polar area problems for you to run into something like cosine squared and sine squared. So I just wanted to make you aware of these, I guess, double angle identities that allow you to integrate cosine squared. You know, cosine squared becomes 1 plus cosine 2 theta over 2, and sine squared is 1 minus cosine 2 theta over 2. So, you know, heads up in case you forgot that. That's the formula for how you work those out. All right, on to the next problem. What I want to do is find the area inside one leaf of this rose, the sine of R is equal to the sine of 5 theta. So let's bounce over. It's kind of pretty. This is what it looks like. It's a beautiful rose shape there. I guess that's a rose. And this is what it looks like as you increase theta. I'll even like make the line there. You can see theta sweeping out, and you can see it drawing out that rose there. So this is what it looks like as it all draws out. You can see this kind of there was like a toy called a spirograph that kind of reminds me of that, if you guys remember that toy. It's probably before your time, but so this is what we want, just that one leaf right there. So somewhere around pi 0.63 is where we're going to get one leaf. The hard part about this problem is figuring out what the values are that are going to cause R to be 0. I think you can see when we start making this leaf right here, R will be 0. And then what we're doing is we're tracing out a part of it until boop, right there. I don't know, somewhere right there where we get another R value. Okay, so let me make that little table. Okay, so I've worked out a pretty general solution here. The actual solution is a little bit more simple than the work that I've done, but you know, I just wanted to show you the full case. So what we're really looking for is two places where R is equal to 0, two adjacent places, one where R is equal to 0, and then it's going to go around and make one leaf, and we'll get another R is equal to 0. So if we want R to be equal to 0, then that happens. Remember, R is equal to sine 5 theta, so that means that 0 equals sine 5 theta. And there's two places where 5 theta could be equal, two values for 5 theta that could make the sine of 5 theta equal to 0. You know, the sine of 0 is 0, and then also the sine of pi is 0. But remember, it keeps going around. You know, any multiple of 2 pi also will produce values where R is equal to 0. So I've solved these in general. All you need to do is really pick any two adjacent ones. So I pick the ones here where K is equal to 0. So I just kind of picked the first two. That is just this first leaf right here. You can see I have just made one leaf by going from 0 up to pi over 5. But if you wanted to, if you chose like k is equal to 1 or something, then that would find the area of this leaf, and then if you choose k is equal to 2, then that will find the area of this leaf, So there it is in general. But in this problem, let's just sort of keep it simple and just use the first two values for theta. But again, the logic is the same here. Really, all you're doing throughout all this process is just, trying to find one time where going around makes a complete version of the object you're looking for without like any duplicates. You don't want to go around twice. Okay, so I'm doing pretty good here setting up all these integrals. Basically, now I'm imagining a laser beam shooting out from the origin and going out until it intersects the curve. So I chose r is equal to 0 because r equals 0 is part of the leaf, and then it goes out until it hits that curve right there. So that's why I got r is equal to sine of 5 theta, and then there I'm going from the 2 thetas that I found by finding the place where r is equal to 0. So, there's a lot of variations of these problems, and a lot of this content is also buried back in trigonometry. So if you're doing these and you get stuck, if you have a weird one, just let me know and I'll see if I can give you a hint.